We talk about the kind, nature, and types of nuclear entities involved in nuclear reactions, i.e., decay, emissions, absorptions, excitation that can be angular for a nucleus, or ejectory for a nucleus, or de-excitation, which can be either the conversion of a radionuclide to a non-radioactive nucleus or a radioactive nucleus, whereby a non-radioactive nucleus may become radioactive after losing a few nucleons, and vice versa. So all nuclear events are stochastic, randomized, and are governed by the mass defect equation E equals mc squared. So what are nuclear entities? These are, sorry, that's why it was very difficult. That's why I wrote it earlier. So nuclear entities are particles, atoms, nuclei. These are particles, atoms, nuclei, and photons. I'm not going to talk about phonons because they pertain to longitudinal sound waves, so I'm not going to talk about them. There's a graviton as well, and there's thermion for temperature exchange. But I'm not going to go there. Let's not go there. So particles, these are atoms, nuclei, and photons that are involved in causing the radionuclide to decay or to emit further particles, i.e. proton emission, neutron emission, alpha emission, or to lead to absorption of proton absorption, positron absorption, or lead to its excitation, whereby the nucleus may undergo angular excitation, which means that it may not emit anything, but its axial rotary velocity may increase, which may lead to a higher momentum for the atoms of that element, and for that block or piece of, it may get heated or experience thermal excitation, or it could be ejectory radionuclei, ejectory radioactive excitation. And de-excitation could be, it could get, it wasn't, so prior to de-excitation, it was radioactive, but after that, it turned into a non-radioactive metal or an element, or a non-metal for that matter. And de-excitation to a radioactive state is whereby it wasn't radioactive, but after getting, deleted from a few of its nucleons, it experienced a transmutation into a radioactive isotopic form. All nuclear events are stochastic and randomized and are governed by the mass defect equation. There we go. That's that. And so now you can have, so for example, 2 protons and 2 neutrons. They, 2 protons and 2 neutrons is an is a helium nucleus. It's not an helium atom, but it's known as an alpha particle, which is double charged, double ionized. So and a single electron would be a beta particle. And photons, now let me tell you something about photons. Photons are characteristic emission signatures. I think it's time for this to go. Characteristic emission signatures of EM waves. So each EM wave, microwave, radio waves, X-rays, UVA, UVB, UVC, all of these waves have their own characteristic photons. Now photons have no mass, no weight, because weight is a product of the gravitational force, and the mass, product of mass and its gravitational force, and they don't have, they are accelerating indeed, and they decelerate as well, and they experience velocity, and they experience a decline in velocity as well. They convey energy, but don't have any weight, so the gravitational constant does not apply. That's that. So now we've got single particles, and we've got a group of particles, and we've got EM wave photons. These are the three major chief nuclear exchange particles. In addition to that, you've got other particles that are classed as quarks, that also lead to exchange of nuclear characteristics and are covered by quantum chromodynamics. And then you come across particles such as antimatter particles that are basically opposite of the matter particles, protons, electrons and neutrons, and antineutron, and they have opposite characteristics and antimass, so they are another family of particles that can induce or is produced as a result of nuclear activity. That's that. But one of the aspects I wasn't able to cover in my previous video, Nuclear Chemical Reactions Part 2 of 2, was the idea of different types of nuclei, types of nuclear variation. That was to, or more should I say, the types of nuclei. The types of nuclei that I wanted to talk about, but what I couldn't because of my intention to keep the video short, less than 15 minutes, was the idea that when I told you that this isotope or this element was most likely oxygen or carbon or nitrogen, I didn't clarify that it could be, there are three different kinds of nuclei. One is an isotope. Now, I'm not going to go into physical chemistry where, we talk about isotope, allotrope, but it's a bit similar, but it's quite different. And then isobars and isotones. Now, that's 1, 2, 3. So, I wanted to just talk about isotope, isobars, and isotones. In isotopes, it's the most common one, and isobars are nuclei with the same atomic number, same atomic weight. For example, carbon carbon 14 and nitrogen 14. So one has 6 protons and the other one has 7 protons. So they differ in number of protons, but they don't differ in number of nucleons. So the total number of, the bottom one is different, but the top part isn't. So Z is same, but the atomic number is not the same. Now we move on to isotones that are nuclides with the same number of neutrons. For example, these are different elements: carbon, and oxygen. So oxygen 16 and oxygen 16 and carbon 14. Both of them would have the same atomic number of protons. That's quite interesting, and that happens in real life. It is part of real laboratory work. So this is equal, but that's not. So in this case, is not equal, but this is. So I think I hope I get my point across. Isotopes are the most commonly used in physics questions where there is the Z is equal charge Z. Sorry, they have equal charge. Sorry, the charge would be not Z in this case, but Q, Z, and A. So they have, for example, they're the same element with the varying number of nucleons and the same atomic number. Isobars are different elements with the same nucleon number but varying atomic numbers, and isotones are different varying elements with varying nucleon numbers and same atomic numbers. So let me just recap that. Okay, so wonderful, fantastic. I've written it down for you. So isotope is a name given to the phenomena where elements, it's the same element, carbon, oxygen, bismuth, titanium, tungsten, magnesium, calcium, francium, cesium, strontium, lithium, sodium, calcium, iron, lead, hydrogen, copper, whichever, but it has varying nucleonic numbers, i.e. the top part, but it has the same proton number, the bottom part. So carbon 1416, but it's 66 at the bottom. Isobars and isotones are different to isotopes because both of them are about different elements. So just like in immunity, you've got xeno, auto, iso, autogenic, xenogenic, and isogenic. You've got isobars, isotones, and isotopes. Isotopes about the same element but varying nucleonic numbers and same atomic number. But isobars are about varying elements with the same nucleon number and unequal proton number. However, isotones are about varying elements and same atomic number but varying nucleonic number. So let me repeat, isotopes are the same element with varying nucleonic number, same proton number. Isobars are varying elements with equal nucleon number and unequal atomic number. Isotones are varying different elements with same proton number and different nucleonic numbers. So same element, different element, different element. And so isotope, isobar, isotone. Isotope, same element. Isobar, different element. Isotone, different element. And that's how things are. I hope you'll be able to make notes and understand the difference between these three entities, nuclear entities, isotopes, isobars, and isotones. Thank you very much. Have a lovely day. If you've got a question, please post it at the bottom. Thank you very much. Have a lovely day. Take care. Bye now.